in the previous class, we discussed about the osmotic pressure and how using osmotic pressure we could determine the molecular mass of an unknown solute, and we proved that the osmotic pressure is a colligative properties. So today we will discuss about abnormal molar mass with respect to the determination of the molecular mass of an unknown solute from the colligative properties determination. Abnormal molar mass. Okay, so why the abnormal molar mass? Properties of the solution which depend upon the number of particles of the solute inside the solution are called the colligative properties. So, number of particles inside the solution is very important. Okay, we studied a number of colligative properties, 4 colligative properties, and also derived their formula. Okay, and the formula were like this. The first colligative properties was the relative lowering of vapor pressure. The relative lowering, capital W, small m. Okay. Similarly, the elevation in boiling point. The elevation, small m, capital W, small m, capital W. Similarly, the depression in freezing point, capital W. And the fourth one is the osmotic pressure, the osmotic. These are the 4 formulae of 4 colligative properties, and in each formula has their molecular mass at the denominator, and suggesting that the molecular mass is inversely proportional to the colligative properties. In each formula you see del P, here is M, del Tb, here is M, pi, here is M. So colligative properties is inversely proportional to molecular mass, the molecular mass. Okay. So let us take an example which shows how molecular mass affects the colligative properties. Now let us take 2 elements and compare their atomic mass with respect to the mole, and accordingly we can conclude how the molecular mass affects the colligative properties. How? Let us take 2 elements. One is sodium, whose atomic mass is 23, another is calcium, whose atomic mass is 40. In case these 2 elements, let us take 10 gram of each sodium and 10 gram of calcium. Okay. So as you know, 1 mole of sodium, 1 mole of this sodium is equal to 23 gram, and 40 gram is the 1 mole of calcium. Okay. From the mole concept. So let us calculate the number of particles in 10 gram of sodium and 10 gram of calcium. So you see 23 gram of sodium is equal to 1 mole, and that is equal to 6.02 into 10 to the power 23 number of sodium atoms. So if we calculate 10 gram of sodium, then that will give us 6.02 into 10 to the power 23 by 23 into 10, and if you that will simplify it, and it gives almost a half of 6.02 into 10 to the power 23. Whereas if we calculate, you see 40 gram of calcium gives you 1 mole, means 6.02 into 10 to the power 23 number of calcium atoms. So that if you calculate 10 gram of calcium, that gives you 6.02 into 10 to the power 23 by 40 into 10, and if you simplify, it gives you almost 1 by 4 into 6.02 into 10 to the power 23. 1/4 of 6.02 to 10 by 23, half of 6.02 to 10 by 23, which is small. So this is a small number, so its molecular atomic mass is higher. So greater is the atomic mass, smaller will be the number of particles. now we are going to get the conclusion. So, when less is the number of particles, less will be the colligative properties, because colligative properties is directly proportional to the number of particles. Higher is the number of particles, higher will be the colligative properties. Smaller will be the number of particles, smaller will be the values of colligative properties. Okay, so next thing is, if we consider atomic mass into molecular mass, similarly we can get higher is the molecular mass, lesser is the number of particles. So from the element we can consider the compound. Okay. If less number of particles implies small value of colligative property. Small value of colligative property. Small value of colligative property. Okay. Small colligative property means molecular mass will be larger than the expected, because we have already told that the colligative properties and molecular mass is inversely proportional. In case colligative properties is smaller than it is expected, then implies if small is the value of colligative property, higher will be the molecular mass. Higher will be the molecular mass of solute than the true value. This is what we call the abnormal molar mass. This we call abnormal molar mass. Abnormal molar mass. Are you getting me now? So, this is the reason why abnormal molecular mass is an important factor to be discussed. So, why there is less number of particles, or sometimes we can also see why there are that means larger number of particles than we actually added. It is very clear to next. So next thing is to discuss is that why less number of particles than we added, or why more number of particles than we added. So let us first discuss why less number of particles is obtained than we actually added. And as you know, some of the compound remain in associated form in particular solvents. For example, benzoic acid. If we take benzoic acid, okay, it remains in dimeric form. Means some of the molecules remain in dimer. Two molecules combine to give one entity. Okay, one molecule, one giant molecule. So benzoic acid, since remain in dimeric form, if you take here, if you have added, for example, 1000 benzoic acid molecule, so you are not going to get that 1000 molecules. Some of the molecules remain in associated form and some remain in unassociated form. This is to be discussed in the next part called the degree of association or dissociation. But it is now clear, since some of the particles remain in associated form, if you have added 1000 number of molecules, then you are not going to get that 1000 molecules, and the total number of particles must be less than 1000. Okay, so here begins the story. So once the number of particles added becomes less than it is actually added, then the colligative properties will be less. Once colligative properties is less than expected, then molecular mass will be higher than the expected, hence the abnormal molar mass. Are you getting it now? So see, this is the dimeric form. That means this is the case of association. This is the case of association. Okay? Got it. Okay. So now it's clear. We have told already that since less number of particles, less will be the colligative properties. So since colligative property is less, molecular mass will be higher, the molar mass. And it should be implies molecular mass of solute should be higher than expected or than true value. Are you getting it up? So, this is the reason why abnormal molar mass. So, same case can be now discussed for dissociation. Okay? Simply we can take the case of sodium chloride. As you know, sodium chloride dissociates into Na plus and Cl minus. One molecule dissociates into two particles. So definitely it is clear that the number of particles inside the solution will be higher than it was actually added. So this is a case of dissociation. This is a case of dissociation. And since dissociation, the particles, the total number of particles becomes higher. So since the particles, number of particles becomes higher, that means the colligative properties will also will be higher. Since colligative properties becomes higher, the molecular mass becomes less than the true value. Here also we get the abnormal molar mass. Colligative properties higher means the molecular mass will be less. Are you getting it? So this is the two cases. To adjust, okay, to adjust this abnormality, this disadvantages, Van 't gave a factor called Van 't factor. This Van 't factor will adjust the increasing or decreasing molecular mass and will bring that molecular mass to the true value. Okay, how? We'll see. Consider the depression in freezing point. Okay, so the formula is del Tf is equal to Kf molar depression constant into W mass of the solvent added to the solution into 1000 by small m molecular mass of the solute into capital W. Okay. So this is the formula of the depression in freezing point. So accordingly, take the molecular mass here, the molecular mass of the solute, we get Kf into W into 1000 by del Tf into capital W. So, case 1, association. So in case of association, total particles after the addition becomes less. So since the particle numbers becomes less than it was actually added, hence the colligative properties also becomes less. And we have already mentioned, once colligative properties becomes less than it should be, then molecular mass will be higher than it should be. So since that means this, in case of association, this becomes higher than expected. Higher than expected. In case of association. So, that means the true value is less than this value. We are saying it is higher, no? Then the true value is less than this. So to get a less value, we must multiply a fraction which is less than 1 with this, so that this value will approach the true value of the molecular mass. Are you getting it? So Van 't Hoff suggested a factor called as I. Van 't Hoff suggested a factor called that means known as I. Van 't Hoff factor. This is Van 't Hoff factor. Okay. This Van 't Hoff factor is called I. It should give now in this case of association is a value that is less than 1. Okay. So that the molecular mass will be smaller and that will approach or that will be equal to the true value. So now, what is that I? Van 't Hoff said I is equal to, Van 't Hoff said I is equal to the total number of particles, after association or dissociation by actual number of particles taken. Actual number of particles taken. So it is clear, you see, after association, since the number of particles is less than that actually added, so this thing, the denominator is having a greater value than the numerator. Okay. So since the numerator is less than the denominator, so it gives you a value that is less than 1. And once you multiply here, so that means you get a value that is less than this value, and it approaches the true value or becomes equal to the true value. So I, in case of association, is less than 1, and when it is multiplied with the formula, so you get this. So simply put, we have a formula now. You have the formula del Tf, or sometimes you write like this: del Tf is equal to Kf m dash. Okay. So I will just now multiply a factor I here. I'll just multiply a factor I here. So that means now the formula del Tf is equal to I into Kf m dash. Or in any one of the formula derived, that means previously, you just multiply this Van 't Hoff factor so that it will adjust the abnormal molar mass to the real molar mass. Are you getting it? So we can also discuss the same case for dissociation now. In case of dissociation, the total number of particles after addition becomes greater than it was actually added. Once the number of particles increase, then colligative properties will rise. If colligative properties will rise, then the molecular mass will be actually smaller than the true value. So, for dissociation, molecular mass will be smaller than expected. So, to get the true value, since it is now coming as smaller, that means smaller than the true value. So, to get the true value, multiply a factor that will be greater than 1, and when multiply that number with this, that will increase the value of this molecular mass to the true value. Because now we are getting a smaller value. If we want to go to the true value of the molar mass, then just multiply a number that is greater than the what? Greater than 1. Okay, so it is also clear, because you see, in case of dissociation, total number of particles after dissociation is greater than the actual number of particles. This is quite different from the previous case. That was this was less. This is greater. So here, since more number of particles are formed, so numerator is greater than the denominator. So this should be, in case of a dissociation, I is greater than 1. I forgot to wrote that. Note it down. Whatever you have written in case of association, I should be less than 1. In case of dissociation, I is greater than 1. So when you multiply this thing, so since this is a greater than 1, when it is multiplied by this number, the molecular mass, which was going to be small, now becomes higher, and then approach or becomes equal to the true value of molecular mass. So this is all about your molecular mass, abnormal molecular mass, and accordingly you can now solve some numericals. Okay, thank you. We'll discuss in the next class.